Now let's look at another example. We want a function f that takes as input m by n matrices and outputs a scalar value, which is defined as f of a equals the sum from m equals 1, I equals 1 to m, and the sum of from j equals 1 to n of aij squared. So what we're doing here is we're just taking all the elements of A and squaring them and adding them all up. You can think of this kind of as analogous to the L2 norm squared of a vector, but for a matrix. So how do we come up with a function in simpler form that does the same thing? Well, first of all, let's write A in terms of its columns. So let's write A in terms of a bunch of columns, A1, A2, all the way to AN. And note that we could write this as just the sum now from I equals 1 to n of AI 2 norm squared, or in fact, well, even simpler, we'll just write it for now as AI transpose AI. Okay, we could write this like this. This is a little bit simpler already, right? But we want to write this even a little bit more compactly. So let's look at one more thing. If we take A written like this, and look at the matrix A transpose times A, this is going to be a matrix of a lot of different inner products of columns of A with themselves. So the first item, for example, would be A1 transpose A1. The next would be A1 transpose A2. The next down here would be A2 transpose A1, A1, A2 transpose A2, etc., all the way down to AN transpose AN. Here you have A1 transpose A1. And here you would have AN transpose A1. Okay, so this is a matrix now that has all these different inner products as elements of this matrix A transpose times A. We, though, just want the elements where the transpose, we're taking the transpose of AI transpose times AI. And those are exactly the diagonal elements of this matrix. And in fact, we have a function that will take all the diagonal elements of a matrix and sum them up. It's just the trace. So the trace of this matrix here is exactly this thing. And so we can write this entire function as just the trace of A transpose A.